that neither the numbers I'm showing in this diagram nor all the details of the carbon cycle are fully understood. A former student of mine is one of the experts on this, and she will tell you that there really is no answer to some of these questions yet. Scientists are still actively studying parts of the carbon cycle. But we know enough, again, to get a pretty big picture and to get it pretty quantitatively accurate. So here's what the picture looks like. The picture looks like these reservoirs, the atmosphere, the surface oceans, the deep oceans, the biota, and so on, and they contain certain amounts of carbon. Now, I have to give you an aside here on the measurement systems I'm going to use in discussing this carbon cycle. And I'm going to discuss in this lecture only the natural carbon cycle. In a subsequent lecture, I'm going to show you how we humans have altered the carbon cycle so you can understand that. But everything I'm saying here is about the carbon cycle as it existed before human beings began modifying it, basically by burning fossil fuels, which produce carbon dioxide, which goes into the atmosphere. But before I do that, a word about measurement systems. The units in this picture are either in gigatons, Gigatonnes, abbreviated capital G, lowercase t, gigatons if they're a reservoir with an amount of carbon, or gigatons per year if it's a flow. So we've got two things going on here. We've got reservoirs that contain amounts of carbon, and we've got flows that involve carbon moving from one reservoir to another. The amounts are in gigatons, and the flows are in gigatons per year. Now, what's a gigaton, and what's it a gigaton of? Well, giga is a prefix that means a billion. You probably 10 years ago wouldn't have known that when your computer speeds were measured in megahertz, but today your computer's speed, if you've got a good computer, is certainly measured in gigahertz, billions of cycles of operations per second. Giga means a billion. It's the opposite of nano, which means a billionth. Everybody's abuzz about nanotechnology, technology at the billionth of a meter scale. Well, giga is the opposite. It's a billion. So giga means a billion. A gigaton is a billion tons. What's a ton? Well, that's also a little bit subtle. In the United States, a ton is 2,000 pounds. And it's spelled T-O-N. In the rest of the world, a ton is a metric ton in the metric system, the System International of Units, SI system. And in the metric system, a ton is, nice round number, 1,000 kilograms. But a kilogram is about 2.2 pounds. And therefore, a metric ton is about 2,200 pounds. And therefore, a metric ton, 2,200 pounds, 1,000 kilograms, and a US-type ton, about 2,000 pounds, are about the same. Now, they're different by 10%, but that's small enough. I'm not going to worry about that difference. So from now on, when I say ton, you are welcome to think English-type ton, if the kind of tons we use in the American system of units, if you like, and you're welcome to think metric ton. It doesn't matter, because to within 10%, they're basically the same. So I'm talking about gigatons mostly. They're the units used to measure global carbon flows and global carbon reservoir quantities. You may hear other scientists, especially biologists, talking not so much about gigatons but petagrams. And you may wonder what on earth the relation between those two is. Well, peta is a prefix in the metric system that means 10 to the power 15. And so it turns out that a petagram, 10 to the 15 grams, is the same as a gigaton, which is a billion. That is 10 to the 9 kilograms, and a kilogram is 1,000 grams. Anyway, a gigaton and a petagram are basically the same thing. So because a gigaton is a billion tons is a billion thousand kilograms, and a kilogram is 1,000 grams. It all works out. A gigaton and a petagram are the same things if you happen to hear those units. I'm going to talk gigatons here, and then I'm going to ask the last question, gigatons of what? And the answer is gigatons of carbon, not of carbon dioxide. And that's an important thing to get straight whenever you see someone saying, oh, we Americans are responsible for X many tons of carbon dioxide every year. You have to ask yourself, are we talking about tons of carbon or tons of carbon dioxide? Because carbon, when it's tied up as carbon dioxide, has those two extra oxygens with it. And a carbon dioxide molecule weighs, let's see, I'd have to figure this out. The atomic weight of oxygen is 16, so I got 2 oxygens, that's 32. The atomic weight of carbon is 12, that's 44, weighs 44 atomic units roughly. Carbon weighs 12, so a carbon dioxide molecule weighs 44 over 12 times as much as a carbon molecule. So if I have carbon as carbon dioxide, the amount of carbon dioxide I have is 44 twelfths or 3 point something times as much as the amount of carbon I've got. However, in the carbon cycle, carbon is not staying as carbon dioxide. It may be taking different forms. In your body, it's in the form of complicated organic compounds. In the soils, it's in all kinds of forms. In the rocks, it's weathered into different things. It's calcium carbonate in the shells of marine organisms. It takes different forms. And so it makes sense to talk about the carbon cycle not as being about carbon dioxide, but as about being carbon, which sometimes, but not always, takes the form of carbon dioxide. So in my diagram, the reservoir amounts are amounts of carbon in gigatons, billions of tons, a metric or American, doesn't matter, English, and the flows are in gigatons per year of carbon. If you want to convert, for instance, the atmospheric carbon content of 560 gigatons, and remember again, that's natural, pre-industrial, if you want to convert that to carbon dioxide, because it's mostly, but not all, in the form of carbon dioxide, you'd multiply by 44/12 and you'd get the amount of carbon dioxide in gigatons. So that's what this picture is all about, and let's take a look at it in detail. First of all, there's a rapid part of the carbon cycle, and that involves the exchanges between air and water, between air and living things, and between air and soil. One of the easiest exchanges to think about is what happens when you open a bottle of soda and the carbon comes fizzing out into the atmosphere. Or you leave a bottle of soda and it gets warm and even more carbon dioxide comes out and it's lost its fizz. Carbon dioxide dissolves in water. The warmer the water, the easier it is for it to dissolve. And so there is a constant flow of carbon dioxide from the atmosphere dissolving in the surface waters of the ocean. However, there's a nearly equal flow in the opposite direction. And in my diagram, these are represented by a couple of arrows upward and downward representing the exchange of carbon dioxide between the air and the surface waters, and you'll notice the numbers associated with those flows are almost identical. There's some slight imbalances here, but they're all compensated for if you add up all these numbers. So that is the natural carbon cycle. There's one of the easiest parts to understand, the exchange of carbon dioxide between the surface waters and the atmosphere, and that's roughly in balance within a few gigatons. Okay? What are some other aspects of that? Well, plants play a major role in the carbon cycle. Plants take carbon dioxide out of the atmosphere, and they use carbon dioxide, which you can think of as burnt carbon. It's combined with oxygen. They basically use solar energy to basically unburn that carbon, separating the carbon from oxygen, combining with hydrogen from water, and making the so-called carbohydrates, the simple sugars and other carbon, hydrogen, oxygen compounds that we use as fuels and that living things in general use as fuels. And this diagram shows that photosynthesis removes about 110 gigatons a year of carbon from the atmosphere each year. And in the process, the plants release oxygen to the atmosphere, and the original photosynthetic plants are the source of the oxygen that's in the atmosphere. Earth is an unusual planet to have a strongly oxygen atmosphere, because oxygen is very reactive chemically and it won't stay there for long unless something is replenishing it. What's replenishing it are the green plants through the process of photosynthesis. And I want to focus a minute on that number, 110 gigatons per year. That's a big number. It's a lot bigger than the amount of carbon that we humans are putting in the atmosphere from burning fossil fuels, much bigger. But for reasons I'm trying to show you in this lecture, the amount we put in is still significant. I'll come to that in the next lecture. Now, what do plants and animals do with this energy? Well, they use it for cellular activity. They use it for big animals like ourselves that can move around. They use it for actual motion. The energy we get all comes from, quote, burning those carbohydrates, undergoing chemical reactions that convert the carbon and hydrogen that are tied up in the carbohydrates to carbon dioxide and water. We exude the carbon dioxide and water. That's why your car steams up when it's cold on the windows and you're breathing out water. Where was the water come from? It came from the oxygen you breathed in, combining with the hydrogen and the hydrocarbons. There's also carbon dioxide building up in the car. That came from the carbon that was in the fuels. So respiration, this process of respiration, returns some of the carbon from photosynthesis back to the atmosphere. Something like roughly half of it goes back for that reason from the plants themselves, and roughly the other half goes back from the processes of respiration in animals, which have eaten the plants, and also from decay of waste material that we excrete or from dead organisms decaying. And together, all those processes, respiration, waste material, and decay of dead organisms, return basically all the carbon, not quite all, but basically all the carbon to the atmosphere. And back it goes. And so the carbon cycle is almost closed right there in that process. Now, some of the carbon ends up getting stored in soils, in the surface soils associated with the presence of living things or dead matter. So there's a reservoir of carbon in the soils also, a reservoir of carbon in the plants. and in the animals, not as much in the animals as in the plants, and very, very, very crudely, the sizes of those reservoirs, the biospheric reservoir and the soil reservoir, are roughly the same order of magnitude as the size of the atmospheric reservoir. The plants and animals are maybe on the order of 500 gigatons, maybe a factor of 2 different. I'm not sure. The biologists aren't absolutely sure. We could study the Earth enough to get that number, but somewhere in that ballpark. There's probably more in the soil, maybe a couple thousand gigatons, but it's still that roughly same order of magnitude. So we understand about those flows.